We continue our discussion of the Boltzmann distribution and the Boltzmann definition of entropy. In our definition of entropy, we made no reference to contact with a heat path, temperature, or any other thermodynamic quantity. So this entropy, defined as the Boltzmann constant times the logarithm of the statistical weight, is fine for a system in complete isolation and indeed the only relevant thermodynamic parameter. So what happens when we now take our system and put it in contact with a heat bath? In order to understand this, we need a somewhat more general definition of entropy. This definition is worked out in Appendix F, where we consider a system, a large number of replicas of a system, and show that the statistical weight can be given in this form, where each of the subsystems in a particular state are shown below here. And by using Stirling's approximation, we arrive at this result shown on the slide. This is elaborated in Appendix F. And so, in consequence, the entropy can be written as this sum here of the probability, whatever it is, it's valid for any arbitrary probability, of finding a state in the R configuration. Now, we are now at a temperature T. Then, of course, we can use the Boltzmann result, which says that the probability of finding a system in energy ER is 1 over the partition function, that's the normalization constant, e to the minus ER over KT. If we plug this into this definition of entropy here, we obtain, and then remembering that the logarithm of a product is the sum of logarithms of terms, cancelling minus signs and factors of k, we then have for the second term in this where I've not bothered writing out the Boltzmann factor again. Now this sum here is just the definition of the thermally averaged energy of a system in contact with a heat bath, divided by T, of course. So we can then write the definition of entropy now in terms of log Z where the bar means the thermally averaged value of energy. So where before we had the statistical, or the entropy being defined in terms of a statistical weight that was a function of whatever the energy of the system was, volume and number of particles, now in the case of a heat bath, we have simply the entropy defined in terms of the thermally averaged energy. So the entropy is a good quantity for a system in contact with a heat bath. Now let us turn to an application of the Boltzmann distribution just to show how powerful it is and to solve a problem that we will refer to at several points in the remainder of the book. This is the question of how ions distribute themselves around a charged electrode. So let us imagine that we have a pair of electrodes immersed into a salt solution and then a battery. So here's the negative terminal, here's the positive terminal. There's excess electronic charge on the surface of this electrode, the negative electrode here. So let's say sodium ions will accumulate on this electrode if it's a sodium chloride electrolyte, and chlorine ions will accumulate on this one. So let's zoom into the surface of this electrode. So we see that it has an excess of negative charge on it, and this will mean an excess of sodium ions. So let's put delta C plus, the change in concentration of positive ions, near this electrode, and consequently a depletion of repulsed negative ions, chloride ions here. But as we go out into the solution, at some point the two concentrations will become equal again, and they'll be equal to the bulk concentration of the salt C0. So in the case that the ions do not stick to the electrode, which in fact is a rare event, but nonetheless let's take that limit, the ions freely exchanging with solution, they're in thermal equilibrium with the solution, then the distribution of excess charge, by which I mean the excess amount of C plus and C minus, of course it's 0 here, which I will just call delta Q of x, where x is a distance away from the electrode, will be given by the Boltzmann distribution. So one can then write this out, given that the energy as a function of x will just be equal to the charge on the ion times the electric field at some point x. Z is the number of charges on the ion, 1 for sodium, 2 for magnesium, and so on. E turns this expression now into coulombs, and then times the electric field will give us the energy at a point x. I do this both for the negative ions and the positive ions, and then put in a factor 1 into the expression so that when the exponential becomes unity at large distances, the excess charge is 0. So here's my expression for the excess charge distribution obtained purely from the Boltzmann factor. The 2 comes from the fact there is a plus charge and a minus charge. So now I know the distribution of excess charges in terms of this unknown quantity, the electric field. But the electric field is related to the charge distribution by Coulomb's law, or equivalently for an electric potential by Poisson's equation. And Poisson's equation says that the second derivative of the electric potential is just proportional to the excess charge, with this constant expressed in terms of the dielectric constant thrown in. So now we have a differential equation which says that the second derivative of the electric potential is equal to an exponential function of the electric potential. This is a difficult equation to solve, and so we're not going to do it. However, in the limit that the energy of the ions is small compared with kT, and remember this is where we want to be because we don't want ions sticking to the electrode in the first place, so when Ze phi is a small number compared with kT, we can expand this exponential in a Taylor series, and when we do this and retain the first order term in electric field, we then end up with a very simple differential equation that says the second derivative of the potential is some constant times the potential itself. You know the solution of equations of this form, they are simply exponentials, where this constant here I've called LD is the decay length for the electric potential. One can simply substitute this trial solution into this equation and then solve for LD, and the expression one has is given on the slide. Solving this now for 300 degrees Kelvin and Z equals 1, one arrives at this very simple relationship that the screening length, the distance over which the electric potential, owing to unequal concentration of ions, falls to 1 over E of its value at the electrode surface, is just given by this length, 0.3 nanometers, divided by the square root of the concentration in moles. So in 1 molar sodium chloride, the electric field is only felt for about 3 angstroms away from the electrode. That result is a little tricky because at high salt concentration some of our approximations break down. But the bottom line is we can understand the screening of an electric field at an electrode involved in an electrolyte very simply, just using the Boltzmann distribution.